Welcome to the first set of notes that we're going to be working through for the entire chapter 12 and one section from chapter 11. So chapter 12 is all about sequences and series. So today the first lesson is just the basic introduction of what a sequence is, what a series is, what are some of the properties that go along with them. So let's just begin. A sequence, whenever we talk about a sequence, is a function whose domain is a set of positive integers. So we've been dealing with these things since the beginning of this year. It should be pretty straightforward. So let's just take an example of the first. Write out the first four terms of the sequence f of n equals 1 over n. What is the nth term? Okay, so if we start out with 1, we have 1 over 1. So we're going to call that a of 1. We're going to say a of 2 is 1 over 2. We're going to say a of 3 is 1 over 3. So we have a of 4 equals 1 over 4. Or in general, we could say a of n equals 1 over n, which is just like what we're used to. If we wanted to graph this, we would have 1, 1, and then at 2, it would be 1/2. At 3, it would be 1/3. 4 would be 1/4, and so on. As we go further down along, we would be getting closer and closer to 0, which is kind of the pattern that each term goes by. So let's say we had that same function. What if we wanted to write that in a better way? That's not just function notation. So if we're ever writing a sequence, if we wanted to write this sequence, we're going to pull out these funky little things. These are called braces. So this indicates a sequence. And we usually say, we give the pattern that the sequence is going by. So this, in our case for this example, would be 1 over n. Likewise, we could define a sequence of numbers as, let's say, 1/2 to the nth power. So if we wanted to write the sequence of numbers that go with that, the first term would be 1/2, then 1/4, then 1/8, so on and so forth. Where the last term would be 1/2 to the n. So let's try a couple of these. Write down the following 6 terms of the following sequence and graph it. So our first 6 terms here, we're going to have a sub 1 is 0 over 1, so 0. A sub 2 is 2 minus 1 over 2, so 1/2. A sub 3 is 2 over 3. A sub 4 is 3 over 4. A sub 5 is 4 over 5. And a sub 6 is 5 over 6. If we drew the graph of this, so our first one is 0. Second one is, so at our first value it's 0. At our second value, we're at, let's call this, let's go by 1/2. That's 1. So at 2, we're already at 1/2. At 3, we're at 2/3, so a little less than halfway. At 4, we're at 3/4, so exactly halfway. At 5, we're at 5/6. And at 6, at 5, we're at 4/5, which is 80%. Then we're at 86%. And we're getting closer and closer. You can see that as our function keeps going on, or as our sequence keeps going on, we're getting closer and closer to 1. So that's going to be an important thing that we're going to find out. Next up, likewise, just another example. Write the first 6 terms of the following sequence. So our sequence is B, so all of our terms are going to be B. So B1 is, if I plug in 1, I get a negative 2 over 1. So negative 2. B sub 2, if I plug in 2 here, I get a positive 1, because 2 divided by 2. B sub 3 is going to be a negative. It's alternating. this piece right here gives me alternating signs. Alternating signs. So if I plugged in 3, we have a negative 1 to the third power, which is negative, and then 2 over 3, so negative 2/3. b sub 4 is going to be positive 1/2. So b sub 5 is going to be negative, so we're going to have our negative sign there, and then we have 2 over 5. And our last term is b sub 6, so I'll write that next. Negative 1 to the 6th power is positive, and 2 over, so we have positive 2 over 6, which is 1/3. So if we drew our graph here, our lowest point would be negative 2. So at 1, we're at negative 2. At 2, we're at 1. At 3, we're at negative 2/3. So we're already below here. At 4, we're at 1/2. At 5, you're getting the point. Our dots here are alternating sides. So if we look at this function, we're going here, then here, then here, then here, then here, then here. We're still approaching a number, which is 0, but we're jumping back and forth of the x-axis each time. So here, if for an alternating series, which should say alternating sequence. So for an alternating sequence, all that means is the sign changes back and forth. From positive to negative. Moving on. So going to the back side, we have just a couple more examples that we're going to go through, just to get the hang of sequences. So for our sequence of C of n, we want the first 6 terms of the following sequence and graph it. So n if n is even, 1 over n if it's odd. So our first one is 1, which is odd, so we're going to have 1 over 1. So we're going to say C sub 1 is 1. Then we're going to have C sub 2. 2 is even, so we're going to have 2. C sub 3 is odd, so we're going to have 1 over 3. C sub 4 is even, so we're going to 4. C sub 5, 1/5. C sub 6 is 6, because that's even. So this gives us our pattern. Our odd numbers are reducing down by a fractional amount, and our even numbers are going up. So again, if I wanted to graph this, we start with 1, 1, and then 2, 2, and then 3 is 1/3. Okay, that's a little weird. 4 goes up to 4. 5 goes to 1/5, so that's way down here. And then 6 is all the way up at 6. So you see, our even numbers are going up 2 every time, but our odd numbers are shrinking rapidly. So this pattern right here is something else that we're going to encounter because it's not going towards the same number all the time. So let's take a look at 5. Determining the sequence given the pattern. So for A, we can say our A sub n sequence is, well, we have E1, E2, E3, e to the 4th over, we can say 1, 2, 3, 4. So we can say that's e to the n over n. How about B? We can say our sequence of B terms, and let's just say, let's keep our notation the same, braces. Our sequence for B is 1, then 1/3, then 1/9, then 1/27. That is 1/3 to the nth power. Because let's double check. If I plugged in 0, well, if I plugged in 1, I still get 1/3. So I need to shift this over 1. So in order to shift that over 1, what if I just subtract 1? 1/3 n minus 1. Because if I plug in 1 now, I have 1/3 to the 0th power, which is 1. So that works. How about C? We have C of n, our sequence, is, well, let's take a look. 1, then 3, then 5, then 7. So this is going up 2 every time. So we start at 1, and we're going up 2 every time. So our sequence is just 2n plus 1. So let's double check. 2, so if I plugged in 1, I would get 2 plus 1, which is 3. So if I want to get my first term, instead of plus, it's going to be minus. So there's going to be a little guess and check work when you're doing these types of problems. Let's double check here. 2n minus 1. If I plug in 1, I get 2 minus 1. If I plug in 2, I get 4 minus 1. If I get 3, that's 6 minus 1. 4 is 8 minus 1. That works out every time. How about for D? We're going to have this sequence. It goes 1, then 4, then 9, 16, 25. These are our perfect squares. So how could we write out a perfect square? We'll have a sequence of whatever our number is squared. And our last one. For E, our sequence of E sub n is going to be, well, we go 1, then negative 1/2, then 1/3, then negative 1/4. So we want something to be alternating. So in order for it to be alternating, and we want the first one to be positive, we're going to say negative 1 to the n plus 1. This plus 1 means that our first term is even. If it was just n, our first term would be odd, which means it would be negative. Then, how do we get this? Well, this is 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. So that's 1 over n. So our sequence of numbers is just negative 1 to the n plus 1 times 1 over n. So if we're defining something recursively, this word recursively means the next number is related to the previous number. So for example, if you have 6 factorial, now most of you guys have seen factorial before. That's 6 times 5 times 4 times 3 times 2 times 1. Well, if I wanted to generate the next number, if I wanted to know what 7 factorial is, all that is 7 times 6 factorial. It's 1 more each time. So that's what we mean by recursive. And we can have sequences that are defined recursively. So let's take a look at these next 2 examples. Write down the first 5 terms of the following recursively defined sequence. So this says our first value, our first term in our sequence is 1. And then each successive one is defined by the term, or n, times the previous one. So s of 1 is just 1. S sub 2 would be 2 times n minus 1, which is 1. So 2 times 1, which is 2. If I wanted to find the third term, it would be 3, because that's our term, times, what was the previous number? 2. So that's 6. S of 4 would be 4 times 6, which is 24. S sub 5 would be 5 times 24, which I believe is 120. So now we're getting to really large numbers. And S sub 6 is 6 times our previous term, which is 120, which is 6 times 12, which is 720. So there you go. There's a recursive function, or a recursive sequence. Last up with recursive. Here's a very, very famous sequence. It's called the Fibonacci sequence. And it involves 2 terms. So it gives you the first 2 terms, and then says the third term, or the next one after that, is the sum of the previous 2. So our sequence would be 1, then 1. If we add these two together, we get 2. If we add these two together, we get 3. If we add these two together, we get 5. There's our first 5 terms. If I wanted to keep going, 3 plus 5 is 8. 5 plus 8 is 13, 21, so on. This is a very, very famous sequence, and it actually happens in a lot of nature. If you want, I can post a video of the Fibonacci sequence, and we'll go from there. Moving on. So oftentimes with sequences, we want to find out what happens when we add these numbers up. So what we get if we're adding a sequence of numbers up, we call it a sum or a summation. And any summation notation, that means this word, a series of numbers. A series just means the sum of a sequence. So let's say we have a string of our sequence and we put a plus sign in between. We get this notation. This is a Greek letter called sigma, and you read that the sum from at the bottom, this is our starting value, often called a counter, like this is what you count from, 2, and the top part is our finish. And right here, inside this series, this sum is our sequence, whatever A of k is. So let's try this out. Write out each sum. We have the sum from 1 to n of 1 over k. So our first term is 1, so we have 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus so on and so forth. That's what this dot 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 means. Plus 1 over what would be our final term? N. This is our sum. Same thing with k factorial. Let's try the second one. From 1 to n of k factorial. So we plug in 1 first. That's 1 factorial plus 2 factorial plus 3 factorial plus. It's generally we can give the first 3 terms of the sequence. Then we can write dot 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 plus n factorial. N is our last term. Likewise, if I give you the summation written out, we can simplify this down to the summation notation. So we have sigma from our starting value is 1, so we say k equals 1. Our finishing value is 9, so I can write 9 at the top. And then what is this? What's the sequence? Well, 1 squared, 2 squared, 3 squared, so on to 9 squared. So that is k squared. And that's how easily we can rewrite this summation. So instead of continually writing plus, 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 we can just write this, and it means the exact same thing. It saves us a bunch of time. Let's try another one. 1 plus 1 half plus 1 fourth plus 1 eighth plus yada, yada, yada plus 2 to the n minus 1. So we'll write our series, so our sum. We start at k equals 1, and we're finishing at n. We're finishing at n, which is what we want. And then what is this? Well, that's 1 half to the k minus 1. Now, why is this minus 1 there? So in our first term, if we plug in 1, we get 1 over 2 to the 0th, which is 1 over 1, which is what we want. So the last couple bits are properties of sequences and series. So let's just look at a couple. If you have a constant multiplied by a sequence, we can really just say it's that constant times each one of those terms. Or we can just bring that constant number out front. Likewise, the sum of two sequences, the sum of two sequences, we can just separate these out. Same thing with subtraction. And this last one, we can split up the sums of where we're going if we know k equals whatever. If we know j is a number in between n, So let's say this is 9, and we know k is, let's say, 4. So that would be 3 plus 1. So we could do from 1 to n minus 1 to j, and that gives us our middle pieces. So let's try utilizing these along with the properties on the back to do the last couple problems. So the last little bits for sums of sequences or series is if you have the sum of a constant number, if you add up all of those terms, n terms, it's just that constant times the number of terms. That will be the sum. If you have a linear function, if we have 1 plus 2 plus 3 plus 4 plus yada yada yada, that sum will be n times n plus 1 all over 2. We could prove these if we wanted to, but we're just going off. Let's just take these for face value that this is what the sums would be. Same thing with something squared. We have n times n plus 1 times 2n plus 1 all over 6. And k cubed, the sequence k cubed, gives you n plus 1 all over 2 quantity squared. So we're going to use these and the properties you had on the previous page to try these out. So find the sum of the sequence from 1 to 5 of 3k. So that's really just 3 times the sum from k equals 1 to 5 of k. Well, now we can just look up right here. We have this sum of k. So let's just plug this in. We know our n is 5, so that's 3 times 5 times 5 plus 1 all over 2. So 5 times 5 plus 1 is 6, divided by 2. So this is 15, 15 times 3. So this sum is just 45. That's how easy this is once we know all of these. Now, the important part is knowing where to look. So the next one, from 1 to 10, k cubed plus 1. Well, first you want to separate these sums. So we have 10 k equals 1 of k cubed plus the sum to 10 of just 1. So now we have these separated. I know what k cubed is. It's right here. And it's to 10, so I'm just going to plug that in. We have 10 times 10 plus 1 all over 2 squared plus 1 times 10, because that's our 1, and our 10 terms is 10. So if I work this out, that's 10 times 11, which is 110 over 2. So this is 55 squared plus 10. So let's see if my math works out. And that should come out to be 3,025 plus 10. So 335. Last one. From 6 to 20. So how we're going to do this is first we're going to pull the 4 out front. K equals 6 to 20 of k squared. So that gets us our first part, but we want our counter to be starting at 1. So what we can do is if we flip back, it's this last bit. We can do j plus 1. So k equals j plus 1. So what is happening here? Well, if we want to choose a j, isn't that 5 plus, we could say 5 plus 1 equals 6. So this is what we're going to do. It's going to be the sum, k equals 1 to 20, k squared, minus, that's our 1 part, minus k equals 1 to 5 of k squared. Now let's just look at this for a second. We want to know starting at 6, and all of these formulas start at 1. So in order to start at 1, we have to do 5 from 1 to 20 and 1 to 5. If we do those, we get everything from 6 to 20. If we take away all of these, what we're left with is 6 to 20. So now all we have to do is plug in the formula. So we go up to k squared, and we have 20 times 20 plus 1 plus 2 times 20 plus 1 all over 6. And mind you, there's a 4 out front of all of these. There's a 4 minus, we're going to plug in 5. So that's 5 times 5 plus 1 plus 2 times 5 plus 1 all over 6. So to finish this out, this is 20, that's 21, that's 41. So this is where you use your calculator. When you type this all into your calculator, you get 4 times 2,870 minus 55. So when you do that math all out, you get 11,260. Hopefully these notes helped. If you have any questions, we'll answer them in class on Monday. And then if you want to start, there's your homework. If not, that's what we'll be working on in class on Monday. All right, good luck.